All right, good afternoon, everyone. So let's get back to our discussion of convolutional layers. So this equation here summarizes everything. Here we have the input to the convolutional layer, which in this case would maybe be an activation from a previous layer, and the output, and this is the kernel. And the way that I like to think about it is if we focus on a fixed output channel M and a fixed input channel N, then the only thing left that's really happening here is we have a convolution of W over these spatial indices with this image here. So when we learned about those spatial convolutions, so we're essentially doing a separate spatial convolution from every input channel N to every output channel M. So we have a different kernel for every one of those. And then we're just summing across those input channels to get the mth output channel. Okay, so that's what's happening. And let's maybe look at it from another very tangible perspective. So here we have an input image that is color. So typically we write our color images, or we configure them with 3 channels, red, green, blue. And then these are describing essentially what we want to do. I think if I just describe it in terms of the goal, it should be clear, and then I'll describe it in terms of the convolutional filters. So our goal here is to convolve this image with this little red Gaussian blur filter. So what do you think should happen when I convolve this with this? What am I going to get at?
Another picture.
Another picture. Okay, is it going to be color or not? Or black or grayscale?
Grayscale.
Grayscale.
Peaks at when there's red.
When there's red, we should see brightness. When there's not red, we should see darkness. So, looking at this, there's a lot of red in this apple here, so we would expect to see some output image. It's a grayscale image that has light pixels in this region, but maybe dark pixels elsewhere. Okay, and then similarly, we're going to do the same thing for here, but now it's with a green filter, and so we would expect to get a grayscale image with brightness here and then darkness everywhere else. Okay, so that is indeed what we're going to get. So here you can see immediately there's three input channels, RGB, and there's 4 output channels, okay? But the way we can think about our kernel, if you want, is we can think about each one of these as really having this red filter is really, we can think about it maybe, there's like RGB grayscale filters that correspond to red, right? Because red, like in red, green, blue, red is just the first channel. There's different ways to do this. I'll show you exactly what we're going to do, but you could imagine doing this with, like if this is our RGB, and you looked in the red pane, you would see a grayscale image with brightness here, and then when you looked into this green channel of the filter, you would see maybe an all black image. And when you look at this one, maybe you'd see an all black image. And then maybe this pink one is a little bit more interesting because here, to make pink, you would need to use some combination of red, green, and blue that would be non-trivial, right? So that's another way we can view this, and that maybe makes a little bit more sense from how we described the convolutional channel before, because when we have 3 input channels and 4 output channels, we know that we should have 12 different kernels, 3 times 4. And here you can see the 12 kernels that we have. Okay, is that kind of making sense? We're just viewing these 3 kernels together as a color kernel because we're humans and we can see in 3 colors. So it's just a shortcut. But I could have also shown you 3 individual pictures here, the ones for each channel. Okay. All right, so any other questions about about the goal.
So,
Yeah.
for example, in case of channel 0, what is exactly the kernel here?
I'll show you. I'll show you in the code. You'll see. So there's different ways you could make a red kernel, because red is a vague notion, right? One way to make a red kernel is you could make the first channel of this 3-channel thing to be a Gaussian blur, and you could set the other 2 channels to 0. That would be one way to make a red filter.
And will these 3 be the same?
So usually when you have equal red, green, and blue together, it makes white as a color. So in this sense, no, they would not be the same. Those 3 things would not be the same.
Actually, I'm trying to understand
Okay.
that we are saying that one kernel, for example, reddish, so it will give us brightness on the reddish portion of the image, and otherwise it will be dark. And when it will be applied on that green one, green channel, so what is exactly that kernel that we are applying on these 3 channels?
So if we view the kernel in color, it looks like that color image. If you prefer to view it as a RGB triplet, each one is a grayscale, you might see the first one totally dark, R, the second one bright Gaussian kernel, green, and the third one blue, dark. Right, that's one way to make it.
And then that green of channel 0 will, how it will be different from that green of channel 1?
So okay, maybe I was confusing in how I wrote it here. Let me just. Sorry, let me erase this. Try to draw it differently. So you could say this, or you could view that as a triplet of the RGB components that make up red. So if I did it this way, you would see that in the top image, you would have the Gaussian kernel. Now, when I do this for the second green one, you would see, because again, we have red, green, blue, and I want to represent this, I would make that the green channel has a Gaussian blur filter, but maybe I would just leave these images dark, and that would give me this. Right? And then for the next one, the blue one, it would be the blue channel that has the Gaussian blur filter, so RGB, and then the other ones might be dark.
So there will be only 3 unique kernels.
Well, so this is, we're viewing it in color, but you could also think about it as a triplet of grayscale RGB. This is a triplet, this is a triplet, this is a triplet. So in total, there's 12 of these. So there's another pair. So these are, we can either say we have 4 color things or we have 12 grayscale things. Okay, all right. Okay, so yeah, so some of this we've talked about, but let me just give a few more details. So this color image is a tensor of shape 368 by 487 by 3. So this is 368, 487, and then we said there's 3 channels because it's color. And the way that we're representing it here, where you have vertical pixels, horizontal pixels, channels, this is how you write it in NumPy, and when you work with SK image, you work with this format. But that's not useful for PyTorch. For PyTorch, you have to transpose these coordinates. So we have to have 1, which tells us how many images in our batch. We just have a batch of size 1. We have to tell it how many channels this has, 3, and then we give it the 2 spatial dimensions. So you'll see in our code, we actually will need to do some data pre-processing to start with this, and then make it into that format so we can use it for PyTorch. Okay, so then the convolution layer weight matrix is a tensor of this shape. Number of output channels is 4. number of input channels is 3. K1 by K2 is just, you can almost count the number of pixels here. It's going to be 9 by 9. Each of these is a 9 by 9 kernel. And finally, this is the same equation that we saw on the previous slide that explains how the outputs are computed based on the input image and the this weight tensor. And yeah, there's a bias, but in this case, our bias is just going to be 0 because we're not going to add anything. Okay, so is it kind of making sense? All right, so let's take a look at some of the code. So the first thing we need to do, we're saying, okay, there's going to be one image in our batch, and this is the batch shape that we will want for PyTorch. So number of images, 1, number of channels in, 3 rows and columns. And then this is the command where we can change from the NumPy or SK image format to PyTorch format. So this is the transpose command. So you're familiar with transposing matrices, right? If I have a matrix and I transpose it, that essentially means I'm swapping the indices, I for j, right? But when you have a tensor, transpose is a more general thing. It means like you might swap 2 indices, or you might swap all 3 in some way. So this transpose command basically tells you, pick them in this order. First, choose dimension 2, then choose dimension 0, then choose dimension 1. So first choose dimension 2, then 0, then 1. That puts it in this order. Okay? So that's how we get that. But then we finally need to put in this, this extra dimension, and we do that just by saying, now reshape that according to this size. And so it's just going to say, okay, the data is the same. I'm just thinking of it as a 4-degree tensor rather than a 3-degree tensor. So that's what's happening here. And so now we have the format ready for PyTorch. All we have to do is do torch.tensor. Now Torch can recognize it as a torch tensor. And we're printing out the batch shape, and you can see this is what it is. Or sorry, no, I'm printing it in the demo, but I didn't copy and paste over here. But basically, this is the size that it prints out. Now this is where we get ready to make our convolutional layers. So we say number of channels in, 3, number of channels out, 4, kernel size 9 by 9. And then when we instantiate our convolutional layer from our neural network library, we have to tell it those things. And then it creates a model. And it initializes those model with random weights and biases. So now, as we saw before, we have to, well, what we can do is we can just take a look at the sizes that it made. So this is our weight tensor. And when you look at it, it's the shape is 4, 3, 9, 9, which is what we expect. Number of output channels, number of input channels, and then the kernel size. And then if we look at the bias vector, we just know that there's one scalar bias per output channel. There's 4 output channels, so that makes sense. Okay, everybody good so far? All right, so now we're going to make the desired weights because we have to replace the random ones that were initialized automatically by PyTorch. So the way we do this is actually kind of cool. We're going to exploit something that is very particular about these filters we created, which is that what happens in terms of brightness is completely independent than what happens in terms of color. In other words, let's say for this set of 3 filters, the brightness is highest in the center, and it decays in a Gaussian way as you go to the edges. But it turns out that all of the pixels have exactly the same color. They're all red with the same kind of red. Okay, and these are all green with the same kind of green. These are all blue with the same kind of blue, and so on. So what we can do first is just make a grayscale Gaussian blur filter, and then we'll use that. We'll combine that with the different colors later. All right, so let's, okay, I actually said it in the opposite order that we do it. So here's where we make our Gaussian kernel. We just tell it the kernel size, Gauss kernel, we call that function, and we have, how many rows, how many columns. This is the standard deviation. And so G is going to be our kernel. That's just brightness alone, and that's a matrix. Now, what about the colors? So for simplicity, when I was explaining this, I told you about one way to make colors, which is to make this kernel non-zero, according to this Gaussian shape, and then these other kernels exactly zero. But as you'll see, we're going to do things a little bit different, how we actually make the colors. So this is the RGB, so RGB. These are the RGB values that we used to make our red filter. Rather than using 1, 0, 0, we actually use 1, minus 1/2, minus 1/2. So you could say that this filter is definitely sensitive to red, but it's actually kind of anti-sensitive to green. When it sees green, it doesn't like it. It doesn't just ignore it. It actually gives like a negative output. Okay, this is just a choice for how we did it. We could have also done it other ways. These could have been different negative numbers or zeros, but this is just how it was done. And then when we look at the green channel, it's very similar. The green filter. So the green filter has a green channel at 1, the other channel's at minus 1/2. The blue filter, blue channel at 1, these at minus 1/2. And then this pink filter is a half for the red and blue channels and minus 1 for the green. Okay, so these are just different ways to do filtering in the color domain. But notice that this is purely the color description. It has nothing to do with what's going on spatially. And then this is purely the spatial description. It has nothing to do with what's going on in the color domain. And so the way that we're going to combine it is we're going to use PyTorch broadcasting. This is a matrix that describes the color domain. This is a matrix that describes the brightness domain or the spatial domain. What we actually need is a 4-way tensor. We can make that 4-way tensor by using these two matrices. So what we do is we take the Gaussian spatial thing, we expand it to a 4-way tensor, and we just use none, none, which basically is, as we've seen before in other labs and demos, is sort of a way of saying to PyTorch, just like, repeat as needed. And the color weight, this is the matrix here, and then we're expanding this to a 4-way tensor with none, none, and then we're just doing a pointwise multiply. So this is going to essentially create this 4-way tensor that's going to have this going on in the color domain and this going on in the spatial domain. Okay, so it's an elegant little way of doing that. Okay, any questions on that? Okay, so now we finally have our weight tensor. We can just zero our bias, and we load these back into our state dictionary, load the state dictionary back into the model, and then doing a color filtering is nothing more than putting xtorch, our image, through our model to get ytorch, detaching ytorch back to NumPy so that we can plot it. And here are the 4 grayscale images we get out of each channel. And so you can see for this red filter, interestingly, it found most of the red in this orange here. For the green filter, it found most of the green in those 2 apples. For the blue filter, it actually found most of the blue in this apple. And for the pink filter, it found most of the energy in those 2. Let's see, is there, I don't know if there's more to say. I guess maybe what's sort of interesting is if you look at what happens in a black region of the image, you actually get like a gray output. So I don't know exactly what color map was used, but it could be that 0 in these images is gray, and that when you see black, that's actually like a negative number in the output, which is possible because we actually have negative numbers in our filters. So it could be that where you see black here is like where there's, according to this filter that has like this anti-green, anti-blue component, there's actually like that stuff is here, and that's why it's blacker than even the so-called background. Okay. All right, so yeah, and then this kind of stuff is what's happening inside a neural network. I'll show you other examples later. So, maybe this is your input, and then this happens in your first layer. Sorry, this is your first layer of your first convolutional layer, and then the features or feature maps that come out of it might look like this. And maybe these are somehow useful for classification if the color is really important to determining, what's an apple versus an orange versus something else. So this would maybe be useful information for the remainder of the neural network. Okay. Any questions? So just like a tangible example of convolution in PyTorch. So, I said that I would show you what was actually learned for these 11 by 11 kernels in AlexNet in the first layer. And this is what they are. So notice that if we think about the kernels as grayscale, there would be 3 times 96 of them. But we can also visualize the 3 kernels that take us from this color image to the first. We can view those 3 as a color kernel. And then there's going to be 3 more that take us to the second one, and so on. We could view those as a color kernel. And so that is what we see here. We have those 96 different color kernels. And this is what was learned to do classification in ImageNet. And so you find these shapes that are, it's interesting that a lot of the shapes are white, which means that they include red, green, blue components all together, that somehow the features they're creating are not really about color, they're just about shape. And what these are is essentially, if I would look across this direction, I would see things go up and then down and then up and then back to the middle. So it's some sort of little, you could say it's a form of an edge detector where the edge is in that direction. And then here is like a double edge detector when the edge is in that direction, and so on. Here is maybe like some kind of big, maybe this you could say is like looking for a thick edge, and so on. You could come up with your own interpretations of these. And we also have ones that are color sensitive. They're looking for when there's red in this direction and pink in this direction, and so on. Some of them are checkerboard type patterns. But for whatever reason, these are what it found most useful for that very first set of feature maps that would eventually become changed over and over again and finally be useful for classification. And these shapes are actually quite similar to what you find when you look at mammalian brains and you look at what kind of color patterns are exciting the neurons in our V1 layer. They actually look quite a bit like these shapes. So it's pretty interesting that that's what's learned by this neural network also. Okay, any questions on this stuff? All right. Okay, so now we're going to talk about a lot of different tricks that we need to do when training convolutional neural networks or deep networks. And so the first thing we'll talk about briefly is backpropagation. And as you'll see, there's a bunch of notation, a bunch more notation now than the last unit. So try not to get too distracted by all the details. Let's just focus on the high-level stuff. So what we have, in principle, looks a lot like what we saw back in Unit 8. So we have now many more layers, possibly many more layers. So we're going to use L to determine the number of layers. So you can see like these are the activations in layer L-2, L-1, and so on. And this ... means that there's many more of these here, but I'm just not drawing them all. So anyway, for any given Z, which we can think of them as the linear outputs of the outputs of a linear layer, you have the activations going into it, and then you also need to know the weights and biases for that layer, and together those things determine your scores Z. Those scores will go through an activation. Those activations will be used for the next layer, and so on and so on. And so when you think about the total number of parameters, we're going to have weights and biases for layers little l, 1 through big L. And if there's dense layers, they're actually, you can think of a dense layer as a special case of a convolutional layer with a 1-by-1 kernel. So that means that we don't really have to treat the dense layers any differently. We can just think about them as a special kind of convolutional layer, a simple kind. Okay, so this is what the forward pass looks like. So you initialize the first set of activations as your input X, and then you just do this procedure here for each layer little l. So this is just the convolution equation that we've seen a few times. Here's our weights. Now this is the weight matrix for layer L, the activations that are coming out of the previous layer, biases for layer L, and so on. This gives you the scores for layer L. And then those scores here are going to go through the hidden activation for layer L. But we also are going to have this kind of general thing, which is going to represent the subsampling or pooling operation that might be in that layer. So maybe we're going to downsample by 2, or maybe we'll do max pooling or average pooling. And this is a sort of a very general thing here that I'm putting in all the indices because I'm saying what happens here could actually be different for every element within the batch. Because when you go through an average layer, it's actually using it's figuring out what it's doing based on the image. So you can still write it as a linear operation, but it's just that the value of that linear operation may actually be, determined by the exact ith batch element in the batch. And it may be specific to what happens is specific to the output indices K1 and K2, as well as the input indices J1 and J2, as well as the channel M. So everything's in there. It's just a way of writing the subsampling pooling operation that allows us to work with things tractably. Okay. So anyway, this is the forward pass. We go through this. We initialize all our variables, and then finally we have a loss that looks like this. So now this is the label for the ith batch element, and this is the final features that are output by the neural network for the ith batch element, and this capital L is for the Lth layer. And this is going to be a rank 3 tensor, which is made up from that last capital Z. Okay, so that's a forward pass. For the backward pass, the procedure is exactly like what we derived in Unit 8. We use the multivariate chain rule. Here, you just have to make sure that you're summing across, all the different variables that are appropriate. So, for example, when you do DJ dB for the bias for layer L and channel M, you have to sum over all the input channels, all the batch elements I, and all the pixels in the image or in the feature map in that layer. And basically, so this DJ DZL, this is something you can compute based on the cost. If you're doing regression, maybe it's quadratic. If you're doing classification, maybe it's cross entropy. We saw all the equations for this in the last unit. And then all this other stuff is very similar to the last unit, like DZL, DBL, and so on. You would get that from this, and it's very simple. It's just equals 1, and so on. So again, there's a lot of notation here, but I know you guys are capable of going through, and so I'm just going to focus on the high-level stuff. So one thing I want to point out is when you do this, when you compute this gradient, when you look at what remains, it has the form of a convolution or a correlation. So in other words, you have some, we can think about this as if it was a kernel, essentially. We can think about this as the input image to that convolutional layer, and then you can see that based on this structure here, it's really just nothing more than correlation, which is exactly what a convolutional layer does. So the point is, if you build Or if you design like a GPU that's very fast at doing the forward pass, very fast at doing convolution, then it's also going to be equally fast at the backward pass. Very convenient, right? Forward, backward pass have the same structure. They're both based on convolutions. So we can continue and we can look at DJ, DA activation. And once again, you see exactly that same structure, except now we would technically call this convolution because there's minus signs, not pluses, but convolution and correlation are essentially the same. You just need to flip this around, flip it and reverse it, and then once again, you have correlation. So if you have a GPU or some architecture that's good at doing correlation, it's good for the backward pass as well as the forward pass, and so on. So this is just a pointwise multiply here. So basically, we see that at a high level, things are very similar to the backpropagation we learned before, and just that we have a few more variables to keep track of and convolutions to do instead of matrix multiplies. Okay. So that's all I wanted to say about backpropagation. Are there any questions? Anything here? Okay. All right, so we'll just talk about a number of sort of different topics that relate to training. So as we've seen, state-of-the-art convolutional neural networks involve millions of parameters. They require huge data sets for training, like ImageNet is gigantic, like in the millions. Also might require millions of iterations for training. So when you put all that together, you just have to have efficient hardware. Otherwise, you can't do this stuff. So conventional processors, CPUs, are not very good at this. They're not specialized to doing all these convolutions, over and over again at the speeds we need. So shortly after 2012, when there was these breakthroughs, then the people that work on the hardware realized, wow, there's an opportunity for us. They noticed that what was the kind of operations they were performing in GPUs at the time, just for displays, were actually very similar to the sort of things you need to do, in these kind of computations. And they said, well, we can probably just use a lot of that technology and just specialize it. And that's what they did, companies like NVIDIA. And now there's this massive industry of GPUs specifically for machine learning. And this makes a huge difference. So this is a plot from a few years ago, but what it's doing is it's comparing CPUs to GPUs. So let's just focus on this. This is when you have one GPU, and this is the time, so smaller is better. So I think this is the execution time. Let's see. Okay. Okay, let's focus on the blue curve. So the blue curve is showing the speed up against one CPU. So for this GPU, this was 30 times faster than a CPU. I think nowadays they're even faster than that. I mean, CPUs have also gotten a little bit faster, but probably not at the same rate. This is what happens when you have one GPU, but the GPUs can be designed that they work well together, and they actually scale quite well when you have just a few of them. So when you add a second one, the time reduces almost exactly by half, which is what you'd really hope. And now your speed up has actually gone from 30 to 70 times. So now you're 70 times faster than a CPU. When you go to 4, ideally it would be double this. It's not quite double, it's 130, but that's still really good. At some point, the returns are a little bit diminishing by the time you get to 6. It's a little bit faster, but it's not 50% faster and so on. But you can see you get quite a speed up, and to really train these big models, you really do need multiple GPUs. And companies like Google and so on, they have these whole data centers where they have just thousands of GPUs working on these models and being able to do things quickly. These things do cost some money, so if you want to buy a consumer GPU workstation, a nice one for machine learning, maybe you can do this for $3,000. If you want to buy a machine that has multiple good GPUs, maybe 30,000. If you don't want to invest that much money and you maybe just want to play with things, maybe you're a hobbyist and you like to take part in Kaggle competitions, you can rent GPUs for roughly $1 an hour. Now, there's many different kinds of GPUs. If you rent a really fast one, it's going to cost a lot more per dollar than if you rent a slow one or an old one. So this number, $1 an hour, is very rough. I would say this is probably for a very fast one. You could probably do cheaper if you use a worse GPU. But there's many companies that allow you to do this, Google Colab, many others. So if you click on this link, you get a list. So that's so for your final projects, I know that some students do like to take advantage of these resources because maybe they get frustrated that their laptops don't run fast enough. They'd like to train more models. Okay. Any questions on GPUs or anything like this? Okay.